This study focuses on the topic of offline preference-based reinforcement learning, a variant of conventional reinforcement learning that dispenses with the need for online interaction or specification of reward functions. Instead, the agent is provided with fixed offline trajectories and human preferences between pairs of trajectories to extract the dynamics and task information, respectively. Since the dynamics and task information are orthogonal, a naive approach would involve using preference-based reward learning followed by an off-the-shelf offline RL algorithm. However, this requires the separate learning of a scalar function, which is assumed to be an information bottleneck of the learning process. To address this issue, we propose the offline preference-guided policy optimization paradigm, abbreviated as OPPO, which models offline trajectories and preferences in a one-step process, eliminating the need for separately learning reward function. OPPO achieves this by introducing an offline hindsight information matching objective for optimizing a contextual policy and a preference modeling objective for finding the optimal context. OPPO further integrates a well-performing decision policy by optimizing the two objectives iteratively. Our empirical results demonstrate that OPPO effectively models offline preferences and outperforms prior competing baselines, including offline RL algorithms performed over either true or pseudo reward function specifications. Deep reinforcement learning offers a versatile framework for acquiring task-oriented behaviors. However, the RL formulation, whether on policy or off policy, presupposes two critical conditions for decision policy training: an interactable environment, and pre-specified reward signals. To address these challenges, prior research has explored two approaches. Some works have focused on the offline RL formulation, where the learner only has access to fixed offline trajectories for each transition. Others have considered the preference-based RL formulation, where the task objective is conveyed to the learner through preferences of a human annotator between two trajectories rather than rewards for each transition. We study a new problem setting that combines the two directions mentioned above, namely, offline preference-based reinforcement learning. In this setting, the agent can only access an offline dataset and preference labels. A common practice is to directly combine the previous online preference-based reinforcement methods with off-the-shelf offline reinforcement learning methods. This two-step strategy, as illustrated above, typically involves training a reward function using the Bradley-Terry model in a supervised manner, followed by training the policy with any offline RL algorithm on the transitions relabeled via the learned reward function. However, the practice of separately learning a function that explains expert preferences may not directly instruct the policy on how to act optimally. To address this issue, we present the offline preference-guided policy optimization approach, abbreviated as OPPO, which is a one-step paradigm that simultaneously models offline preferences and learns the optimal policy without requiring the separate learning of a reward function. We start by introducing the concept of hindsight information matching. The decision transformer was the first to model the RL problem as a sequence prediction framework, and achieved good performance by training the transformer with a self-regressive objective, conditioned on the existing reward-to-go information in the offline dataset. The generalized decision transformer further extends the reward-to-go to arbitrary statistical information about the offline trajectories. Information matching is a framework for optimizing Z-conditioned policies by forcing the generated sequence statistical information Z' to be as close as possible to the input target Z. Hindsight information matching replaces the predefined Z with statistical data from existing offline trajectories, introducing hindsight information about the future as guidance for the sequence generation process. The reward-to-go in the DT is a specific example of this. The self-regressive constraint on the generated sequence is often more commonly used in practice. If we abstract Z as some embedding of the trajectory, the embedding process itself can also be learned within this framework. Alright, let's get back to the introduction of OPPO. The ultimate goal of OPPO is to obtain a Z-conditioned policy and the optimal embedding Z* corresponding to the optimal trajectory. On top of this, The optimal policy is obtained by conditioning the contextual policy on the learned optimal context Z star. This is an illustration of the overall framework of OPPO. We train the embedding of the trajectories and the contextual policy using the aforementioned hindsight information matching loss on the reward-free trajectories in the offline dataset. We construct the following preference modeling loss inspired by the contrastive loss in metric learning, where Z+ and Z- represent the embedding of the preferable trajectory and that of the less preferable trajectory, respectively. Our basic assumption of designing such loss is that humans normally conduct two-level comparisons before giving preferences between two trajectories. First, separately judging the similarity between trajectory tau I and the hypothetical optimal trajectory tau star, and the similarity between trajectory tau j and tau star. Then, judging the difference between the above two similarities and setting the trajectory with the higher similarity as the preferred one. Hence, optimizing preference modeling loss guarantees finding the optimal embedding that is more similar to Z+ and less similar to Z-. To clarify, Z star is the corresponding contextual information for tau star. Whereas tau star will always be preferred over any offline trajectories in the dataset. It is worth mentioning that the posterior of the optimal embedding Z star and the hindsight information extractor I theta are updated alternatively to ensure learning stability. A better estimate of the optimal embedding helps the encoder to extract features to which the human labeler pays more attention. In contrast, a better hindsight information encoder, on the other hand, accelerates the search process for the optimal trajectory in the high-level embedding space. We also add a normalization loss to constrain the L2 norm of all embeddings generated by hindsight information extractor in total loss. A central premise behind the design of OPPO is that the learned hindsight information encoder I theta can capture preferences over different trajectories. Our experiments are therefore designed to answer the different questions. First, does OPPO truly capture the preference? In other words, does the space align with the given preference? We first sample random trajectories from the offline dataset, and encode them with the learned I theta, and utilize TSNE as a tool to visualize the encoded Z. The learned optimal Z star is marked with an orange dot. Besides, we also the embedding of optimal trajectory in the expert dataset, generated by the learned online optimal policy, with a red dot. As illustrated, the trajectories embeddings that are near red dot often have high returns. Further, we observe that our learned optimal Z star constantly stays close to actual optimal Z in dataset, which suggests that our learned Z star preserves near optimal behaviors. Thus, it gives justification that OPPO can make meaningful preference modeling. Above, we show that our learned I theta can produce a well-aligned context embedding Z-space exhibiting effective preference modeling across embeddings of trajectories. More importantly, context embeddings preference property should be preserved when we condition the context on the learned contextual policy. In other words, not only I theta should transfers the preference relationship to the Z-space, but further, rolling out the contextual policy, the generated trajectories should similarly preserve the preference relationship. We compare the performance of rollouts by the contextual policy conditioned on different contexts. As illustrated, we discover that the contextual policy conditioned on Z with a high, or low, return obtains an actual high, or low, return when rollouting this policy in the environment. Therefore, OPPO preserving the hindsight preference relationship. Furthermore, our learned policy performs the best. We also investigate whether the optimal policy can achieve competitive performance on the offline PbRL benchmark. For comparison, we consider for offline methods and BC as baselines. OPPO has retained comparable performance with only preferences against the baseline methods trained using true rewards. For more details, you can refer to our paper, project page and GitHub by scanning the QR code. Thank you for listening to our introduction.